Hello friends, in this part of video on gravitation, we will be studying about motion of a satellite around the Earth. So our focus will be mainly on the parameters related to satellite motion. So first is orbital velocity, time period, height of a satellite, and then types of orbits and weightlessness. So these are the things we will be studying here. So first let us derive these parameters and then go through a simulation trying to visualize these parameters. So first is orbital velocity. So let us say that we have this Earth of radius capital R and satellite is placed at a height h from the surface. So basically the total distance of satellite from the center of Earth is small r. So assume that the velocity with which the satellite is orbiting is v naught and it is of mass small m. Now satellite can orbit Earth only when its centripetal force required to move in orbit is balanced by gravitational force. So this is the basis for deriving the expression for orbital velocity. So centripetal force is given by mv square by r and the gravitational force is given by g into capital M small m divided by r square. Based on this you can see that v is equal to under root gm divided by r plus h. So what we have done is that simply we have replaced distance of satellite from the center of Earth small r by radius of Earth r plus height of the satellite. Okay, so this is the expression for orbital velocity of satellite around the Earth at a height h. Now we can simplify this expression for an orbit close to the Earth, and this is possible by invoking a condition. So condition is that the height of the satellite is much less than the radius of the Earth. So in that case we can just neglect the h term in the denominator here, and also we know that g into capital M is given by small g into r square. So using that, and since in the denominator h is neglected, we have orbital velocity as under root g into r. So this is the case of orbital velocity, and now we will derive time period. So what is time period? It is the time taken for one complete rotation of satellite around the Earth. So it is simply given by the circumference divided by velocity, because velocity is equal to distance traveled by time taken, and therefore time taken is simply distance traveled by velocity, and therefore we have 2 pi r divided by orbital velocity. So just substitute the value of orbital velocity as we have derived just earlier. So using the orbital velocity expression, what we have is time period as 2 pi into square root of r cube by gm. So I will replace small r by r plus h, and we have the final expression 2 pi under root radius of the Earth r plus h whole cube divided by g into m. Again we in this case also we can approximate it, and also using g into m as gr square, we have a simple expression for time period which is 2 pi into square root of radius of Earth divided by g, that is acceleration due to gravity. The approximation for time period which gives rise to equation t is equal to 2 pi root r by g. So this is valid only for very low Earth orbit satellites, that is for the case of height h is equal to 60 km or 1 by 10th of radius of Earth. But since the satellites in general, the remote sensing satellites are at a distance of 300 to 400 km above the surface of Earth, the general formula T is equal to 2 pi square root of r cube by gm is valid even for those heights which we said, that is 300 to 400 km. So we have derived orbital velocity and time period, and based on this we will also derive the height at which a satellite is placed. So using the equation for time period, and we will just square this equation, and it will be t square is equal to 4 pi square into r cube by gm. So r is the distance of satellite from the center. So now you just write down the expression for r cube, and since r cube is there, so r is equal to gmt square by 4 pi square to the power 1 by 3. Now note that r is equal to r plus h, so the radius of earth r we will shift to the right hand side, so that gives us the height of the satellite, right? So this is the final expression, which is the term in the bracket to the power 1 by 3 minus radius of earth. So now what we will do, we will consider the case of a geostationary satellite. So we will understand in detail what is geostationary satellite, but for the time being you should know that for the satellite placed in geostationary orbit, the time period of rotation of satellite is 24 hours. So it means 24 into 3600 seconds. So with this as the information, and we should also note that radius of earth is 6400 kilometer. So with these two we can just calculate height of the satellite placed in geostationary orbit. Another thing which we can do is, instead of using g and m, we can simply replace it by small g into capital R square. So just substitute all this, and g is equal to 9.8, 6400 into 1000 meter is the radius of earth, so and it is squared, and 24 into 3600 square, which is the time period square, divided by 4 pi square to the power 1 by 3 minus the radius again in meter. So solve this numerical and you will see that it comes out nearly equal to 36,000 kilometer. What I have said is approximated value, but the present calculation yields 35,936 kilometer. So this is actually the height of the satellite which is placed in a geostationary orbit, right? So now, based on these simple parameters of satellite motion, we will now understand or go through a simulation based on this. So we talked of geostationary orbit, so first we will start with that. So a geostationary orbit is placed such that the plane of orbit of satellite coincides with equatorial plane of the earth. Further, since earth is rotating about its own axis from west to east, in the same way the geostationary orbit of a satellite rotates in the same fashion about the earth, and its time period of rotation is the same as time period of rotation of earth about its own axis, that is 24 hours. So this is the basic definition for geostationary orbit. So it's not like for every satellite geostationary orbits are used. And further, you should note that geostationary orbit is called so because it appears to be at rest relative to the earth, and note that in the present case its window is facing towards the Indian subcontinent. And similar way, any other geostationary satellite, let us say launched by a nation such as US, so it may be facing towards a window directed towards that particular country. So this is the idea behind geostationary satellite. Now going to inclined orbit. When the orbit of satellite is inclined at some angle to the equatorial plane, we call it as inclined orbit. Then the next one is polar orbit. So in the case of polar orbit, angle of inclination is 90 degree because angle of inclination is measured with respect to the equatorial plane. Now why polar orbits are necessary? Because low earth satellites in polar orbits are mainly used in remote sensing applications. Remote sensing satellites have widespread applications ranging from agriculture to urban planning. A high revisit time is required so that same location can be tracked continuously. So therefore, the polar satellites are usually positioned near to 500 and 800 km above the earth, and it travels pole to pole in about 100 minutes. So having studied these concepts through animation, let's explore the case of geostationary satellite. So as you can see that the geostationary satellite is perfectly in sync with the motion of Earth around its own axis, and that is the reason we call it as geostationary satellite. And some extra parameters which we have to note here: the kinetic energy is given by g mass of satellite mass of Earth divided by 2 into radius of Earth plus height of the satellite. So that will give us 23.49 into 10 to the power 8 joule, provided the mass of satellite is close to 500 kg. Further, potential energy is minus g small m capital M divided by Re plus H. So that is minus 46.99 into 10 to the power 8 joules. So total energy is simply given by minus gmm divided by 2 into Re plus H. So total energy is again negative, you should note here, because total energy is not negative, then the orbit will not be stable. So this is another condition for stable orbit of a satellite which you should remember. When we say there is stability, then total energy is negative. Okay, so having understood different types of orbits of a satellite, now we will just brush through one important concept, which is weightlessness in a satellite. So consider satellite orbiting with a velocity v, then in that case the acceleration directed towards the center of Earth is simply v square by r, where r is the distance of satellite from the center of Earth. Now if a person of mass is placed in the satellite and the centripetal acceleration is a, which is directed towards the Earth. Now this person feels weight because of a normal reaction, and the normal reaction in the general case is mg minus ma, and because of this he feels his own weight. When the centripetal acceleration becomes equal to g, the normal reaction is 0, and because of that he stops feeling his weight. So weightlessness is a feeling of absence of gravitational field, but in the real sense gravitational field is not absent. So there should not be a misconception that weightlessness implies lack of perception of gravitational field because of absence of normal reaction. So to summarize, we will list all the parameters that we have derived. So the orbital velocity is square root of gm divided by r plus h. Anyway, in all the cases you can replace g into m by small g into capital R square. So t is equal to, or the time period is equal to 2 pi root r plus h cube by gm. Height of the satellite is gmt square by 4 pi square to the power 1 by 3 minus r. Kinetic energy is half gmm divided by r plus h. Potential energy is negative, which is minus gmm by r plus h. So total energy is again negative, which is minus gmm divided by 2 into r plus h. So this is how, by using these simple parameters, you can understand motion of a satellite around the Earth.